So hello everyone. On behalf of the engineering team, specifically Michael, Mauricio, and I wanted to give kind of small updates on the EVM Protocol Adapter development, specifically as we're drawing close to the release. I feel like relevant parties should know what's happening. I will not quite define what an EVM protocol adapter is because Michael did it perfectly, I think, last Hacker House, but I will bring up like small notes. What is a protocol adapter on the EVM? Well, it's an implementation of a Anoma resource machine, of an Anoma replicated state machine really, so something that can create and consume resources on the EVM as implemented on a Solidity contract. In terms of implementation details, it's settlement only. What that means is there's no post-ordering execution. Transactions come in the specified data types. We use the RISC-0 proving system, a specific version of it, in order to check compliance and resource logic proofs. We use Peterson commitment scheme for delta proofs. And finally, we support EVM state interop. What that means is that resources on the resource machine can call out to external state in the EVM, bind it to itself, and ask questions. For example, a resource may now ask what's the current Ethereum block time, or it can, for example, lock an ERC20 token to be available on the resource machine side. So in terms of contents, the large-scale changes sort of eminently fit into three categories. They're resource machine changes, those changes that are Anoma specific. There are changes to the EVM interoperability, specifically dealing with something called forwarder contracts, which I will talk about later. And finally, there is this very much in development hot topic of version management, which I wanted to briefly touch base upon. So let's talk about some changes to the resource machine. A particular one that I think impacts the entire stack is that we have an application data refactor. So app data previously was, for the intents and purposes of this conversation, a list of blobs, just a list of bytes. It was not formatted, and in this sense, for external parties such as indexers, solvers, and the protocol adapter itself, it was hard to structure information. So based on the kind of ever-present demands of the stack, we decided to separate it with the specs team into 4 different components. Specifically, there will be 4 payloads. There will be the resource payload. The resource payload bears information and encodes anything that is connected to resource plaintext. That can include the resource data types itself. It can include nullifier keys. It can include also the pre-images of the logic graph, labor graph hashes, whatever you want, basically. The discovery payload bears blobs whose content isn't as important as the ability to decode those blobs. Into the discovery payload, things like indexers and solvers will look into in order to understand whether the information of a transaction is interesting to them or not. We have an external payload, which is something that is very important to the protocol adapter itself. Specifically, it looks there in order to understand whether it needs or not to perform an external call to another EVM contract. And finally, we have application payload, which is just a general payload for anything that doesn't seem to fit this category. A large one is variable size trees. What I mean by that is we use Merkle trees in 2 cases for this implementation. First one is, of course, for the commitment accumulator. So we store all of the commitments inside a Merkle tree. And the second one is that we actually, per action, store all the created and nullified resources also in a tree. Now, up until recently, we sort of just played with the fact that the size of those trees is fixed sized in order to ensure interoperability with other proving systems, but RISC-0 ZKVM allows us to have variable sized inputs. So for example, the same circuit can accept Merkle paths of different size, and what that led into is the fact that we can use just sparse variable sized Merkle trees that go naturally. By that I mean, like, how do you first learn about Merkle trees? You just start off with an empty sparse hash. When you fill that up, the tree expands to now depth 1. You fill that up, it now needs another depth, and you can go on adding commitments as you want. The idea is basically we just use trees as big as necessary in order to store commitments and provide these services. This has two impacts. So for the action trees, previously the depth was sort of agreed to be 4, and that meant that we could only store as many resources, right? You could only store as many resources in an action, create and consume, as how many leaves you have in that tree. Now actions are arbitrary sized, so you can create and consume as many resources as you want per action. On the commitment accumulator side, we now don't have a huge 32 depth tree, which means that this actually introduces huge gas cuts. So this is not an official info, but our preliminary benchmarks show about a 33% cut in gas prices now. So this is an active integration, and official benchmarks will come soon. Now we come to the EVM interoperability part of the conversation. That part is pretty technical, but what we need to know is how does the resource machine talk to outside the Ethereum contracts. There should be an agreed to interface about how they do it, and this interface comes from so-called forwarder contracts. These forwarder contracts connect RM in EVM state. They can, for example, just again allow you to get the current time, or they can lock funds inside of them in order to make available in the resource machine, so there's a commonsensical binding between the two. The forwarder contracts can execute arbitrary logic, and they also control for kinds. So a resource logic itself controls which sort of external calls that it can make using the logic. And likewise, the forwarder contracts also control which applications can call them. You certainly don't want a forwarder that stores financial assets to be callable by any arbitrary resource, because its rules of creation and consumption may impact the logic. And so that's what the interface is, or rather was. So before we checked for an assumingly unique resource kind, and if the resource kind actually matched the resource that is calling it, then we would execute a forward call with an arbitrary input. However, we found it to be too restrictive, and there are several reasons for that. Firstly, it became harder and harder to sort of justify why forwarder contracts are connected to kinds rather than logics. Secondly, there is a question of the fact that some external calls seem to be something that can be performed by any contract whatsoever. So for example, any resource can ask regarding the current Ethereum timestamp that doesn't interfere with any state whatsoever, and it seems an overkill that every application that wants to use a timer needs to develop its own forwarder contract application. So what we did is we allowed several kinds per forwarder. So now the interface is very minimal. The only thing that you get from the verifier are the inputs, which are basically user provided, and the logic reference that the verifier makes sure is the logic reference of the resource making the call. So as you can see here, for example, that you can theoretically, if the logic so desires, put some label into the input and check its correspondence, but in reality, this allowed several kinds by sort of suggesting that you don't need to filter via label. But moreover, you don't need to support only one logic. So now you can theoretically make a forwarder that accepts any resource to make that call, or a very specific sets of logic. For example, and this is an important one for us, if we want to have a shielded transfer application, there should be a forwarder contract that allows us to lock funds. Now, suppose we have several logics, which basically implement the same strategy of allowing the users to lock ERC20 tokens. The denomination is by design stored in the label, right? Now, before, when there was a unique kind per forwarder, we need to deploy a separate forwarder contract per an ERC20 token in order to support it. Now, the label can be permissionless, and so you can support several ERC20 tokens. But moreover, if we change the logic a little bit by saying that it's not only the transfer logic, but we also require, I don't know, a JPEG of a cat inside the app data to be present in order for transfer to be completed. We can add this as a possible logic calling this contract because it doesn't interact with the state itself. So this minimizes the issue, but the original design can be rescued from that. It's a big change, and I know this is very abstract, but the good news is general things. It's good. A more technical one, and I don't want to get too much into this, is now consumed resource can make calls. Previously, only created resources could make any calls to the external state on the EVM, and that introduced hardships in designing applications. Usually, the minting and burning logic is positioned on separate branches on the consumed and created side, and because we supported only the created resource making the calls, it was hard to design appropriate applications. So don't mind the code. But the important part is in order to make the call, you need to reveal the resource plaintext and make sure that it corresponds to the tag. And yes, nullified resource can now make calls. However, that means that you have to reveal their nullifier key. So the app developer has to be very careful about that. And finally, we come to version management. So the resource machine is hard to manage in terms of versions. Practically speaking, it's an immutable state machine. It's designed to be shielded, and so we cannot provide a direct state migration in if there are any breaking changes. It's really hard to talk about version management, and we don't have a finalized design yet, but I wanted for an internal audience to sort of start the conversation in order so that maybe somebody has more ideas about it, and for the external audience to, be explicit in the fact that we're considering a lot of different scenarios. So I wanted to start with, well, I termed the slide motivation, but it's really about what do we really want from a version management system from the protocol adapter. So the first thing we want is critical bug management. So if there's a critical bug found, we want to be able to stop its exploitation, right? So in some way, if there is a problem with the protocol adapter, we should be able to stop it. And we also want to allow for smooth non-breaking changes, right? So if we want to just add extra functionality to the protocol adapter, we should be able to do so without the developer screaming in agony. So the critical bug management can be on the PA level, and what that means, and I mean here I'm talking both about deploying the protocol adapter as a Heliax product and as something a user would be interested to do, right? We're deploying a protocol. We will deploy as Heliax a protocol adapter themselves, but other users should be able to deploy their own protocol adapters and their own implementation. And what we have to be considerate of is people make mistakes. And there should be a management system that allows both us and users to manage critical bugs if they appear in the code, even after contract deployment. And there are also verifier level bugs. So we use, for example, so the resource machine has been designed with a pluggable proving systems in mind, right? And what that means is that we are happy to use other people's proving systems in order to help us. So for example, we use a RISC-0 verifier. And RISC-0 sometimes may have bugs, and that's what actually happened in development. And what that does is that it practically, for all practical purposes, shuts down the protocol adapter. However, an important point to make is that the forwarder contracts, as they need to bind EVM state, need to be very closely tied to a specific address of the protocol adapter. And that means that the verifier shuts off, the funds may get locked. However, we mitigate this with proper council management, and but this is an important thing to note. For the smooth non-breaking changes, what sort of thing do we want to do? We want to possibly add external functions. So the cryptography team is working, for example, on an aggregated proof of transaction execution, which allows us to basically submit just a proof that a transaction passes all the checks instead of making them manually, which saves a lot of gas. We should be able to just add this function on top of the current functionality, and the users on their side not noticing anything other than the opportunity to now submit a transaction that costs much less gas. And we may want to, I don't know, reset tree depth size. As we now may support variable size trees, they can grow so much that possibly it becomes very, at some very distant point in the future, becomes very costly to upgrade the tree, so maybe you want to reset it. And this made us think about several roles on the PA and on the forwarder in order to mitigate all those issues. On the PA, we might want something of an emergency stopper actor, and the upgrade council, which may propose non-breaking updates. And on the forwarder, we want an emergency council. And what are their semantics? The emergency stopper takes care of the critical bugs if they're found in the system. The upgrade council deals with non-breaking changes, at least we hope so. The emergency stopper should be fast in order to stop exploitation of the bugs. The upgrade council should be slow and deliberate in its proposed upgrades. Moreover, there should be, of course, a decision delay period, because we can say that the upgrade council can propose non-breaking changes, but there is no deterministic way of understanding if that's the case. So on the forwarder, on any sort of EVM state binding, that should be an emergency council that can decide on the app level to veto any such decisions. Now, again, these are not finalized decisions, and these are like recommendations that we're trying to figure out exactly how to implement, so I didn't give out an explicit presentation plan, but these are the roles that seemingly fit our version management strategy. And this is a slide that should represent what the developers and the users should do in case a non-breaking change just works. They should do nothing. The entire version management strategy that we're trying to think of is that if there is a non-malicious change that is proposed and the user and the developer can verify that it's non-malicious, they shouldn't do anything. So only action that is required is when something goes wrong. And I think that's the correct strategy that we should be pursuing. And so with that, I'll end my talk. Thank you so much. Here you can go to the EVM Protocol Adapter GitHub page. We're in active development. Thank you.
All right, thank you, Artem, for telling us all about the protocol adapter and recent improvements. Any questions for Artem? Protocol adapter, 100% clear. You could write it tomorrow. Yes, Patrick.
One of the things that you mentioned earlier in the talk, Artem, was this notion of a settlement-only protocol adapter. What does that mean exactly?
So we have this idea of post-ordering execution, basically, that a replicated state machine can accept a not fully formed transaction. What that means is when you form a transaction, it's formed against a specific timestamp, right? It's formed against a specific route. Now, something that some applications, such as voting applications, may find really important is that they work with the latest information. And that latest information isn't at the time of the composition of the transaction. Well, it is, but we would want possibly for replicated state machine to create these routes at the time of block execution, basically. Right? When the ordering actually was assigned to that preformed transaction. And that's what we want to support in the future, but for deploying it as just a Solidity protocol adapter, the gas costs are too high, right? In order to have post-ordering execution, you basically have to generate proofs on the fly, and that's, of course, currently at the very least impossible on-chain in any productive manner.
Any other questions? All right, let's give it up one more time for Artem.